Hello students and welcome to the online video lecture for this solar and wind energy. In the last lectures, we have discussed about some of the basic topic, that is the principle of the wind energy conversion, these basic components of the wind energy conversion system and its various types. So that we have discussed in the previous lecture. We also discussed about the wind energy potential and the installation in the India. In today's video lecture, we will discuss about some of the design considerations of these two types of the wind turbine, that is horizontal and the vertical axis turbine, and we will discuss about some of the concepts of this power output. And in the coming third video, we'll discuss about the analysis of the aerodynamic forces acting on the windmill blades, and we will discuss about the wind data and site selection consideration. Okay, so in today's lecture, we will mainly focus on uh, uh, the the estimation of the power output and the design consideration of the horizontal and the vertical axis machines. Okay, so these are some of the key design steps in that should be considered while designing the horizontal and vertical axis turbine. So the first is we have to determine the applications. Second one is the review previous experience. Then we have to select the topology. Preliminary load estimate, develop the tentative design. We have to predict the performance, evaluate the design, estimate the cost and the cost of energy, refine the design, build prototype, and test prototype, and last one is the design production machine. So here, these are some of the descriptions for all these type of the design considerations. So design applications means there are two types of the design applications we can consider. One is the utility networks, and another one is for the remote communities. For utility network, the power range is in the range of the 500 to 1,500 kilowatt, while for the remote communities, it is in the range of 10 to 200 kilowatt. If we that means if we are old in the that means we if we have the experience in the designing process, so we can take the help of some of the concept or the mistakes from the previous design, and not only the mistake, but also the if any modifications you have made in the earlier design that are helpful for the increasing the efficiency of the wind turbine, so that we will consider in the current design also. The third one is it is the selection of the topology. The selection of topology is in the form of the rotor axis rotation, power control, the rotor position, yaw control, then the rotor speed, design tip speed, ratio and solidity, and the types of the hub and the number of the blades. Okay, so these are the things that can be considered. So wherever we are using, suppose the horizontal type of we are designing the horizontal type of the wind turbine, so we have to we are the following characters will be changed as per the see for the following the parameters will change as per the designs of the horizontal axis turbine. When we are considering the vertical axis turbine, so again there will be the change in the design process of the following components. The fourth one is the preliminary loads estimate. Now, preliminarily, the estimate that means the load that the turbine must able to withstand. So that means the loads will serve the input to the design of the individual components. Estimation of the load at this step may involve the use of the scaling of the loads from turbines of the similar design. Okay. So here in this case, it is important to keep in mind all the loads that the final turbine will need to be able to withstand. So that we have to consider. This process can be facilitated by referring to recommended the design the standards. So here we have to follow the design standards here. Okay. After that, we are going into we are considering the develop the tentative design. So once all these components are taken into consideration, then we have to go for the tentative design. So once the previous four components when we consider, so that will give you a clear, that means somewhat the clear understanding regarding the design of the turbine, and we can now select the types of the rotor, drive train, nacelle, yaw system, and tower foundation and the erection. Okay, there are also a number of again the general consideration which include the fabrication method, then ease of maintenance, then aesthetics, noise, and other environmental conditions. Okay, now it is always better to predict the performance before manufacturing the design. So early performance, it is early prediction of the performance, it is very effective. So that will give us the efficiency of the turbine and that is calculated in terms of the power curve. Okay, so that is very important parameter. So power curve will give you the what is the maximum efficiency, maximum power that is generated by the wind turbine. We will say what is the we will see what is the maximum limit for this power, and what is the commercial for the wind turbine they generate the power. Okay, so that will that so predict the performance can be predicted by means of here we have the prototype is there, so that will comes afterwards. The evaluation of the design, it is for its ability to withstand the loading the turbine and may reasonably to be expected to encounter. Okay, so we have to first evaluate design. So that is again the same thing that is related with the condition. That means that we can also judge by means of carrying the analysis in the analysis software like FEM. Okay, so the the loading conditions and the effect of the various components like stress. Okay, then the speed of the rotor. Okay, so that can be easily predicted by means of the this type of the software. So that is under the evaluation of the design. Estimate costs and the cost of the energy. So this we can calculate as the theoretical also. So by predicting the performance by getting the values of the power, the velocity and the other the parameters. So it is very easy to calculate the cost of the energy as well as the what is the cost of the design will be there. So that also we can predict. So that is the estimation of the cost and the cost of the energy. Sometimes suppose if while predicting the performance of the design, if we feel somewhat the changes is required in the existing design, so that we can do. So that is the refine of the design. Okay, and then after we will build the prototype based on the the whatever the design parameter we have considered for our wind turbine. Once it is the design is final, so we'll go for the prototype, and then we'll test the prototype in the actual working conditions, and we'll check that the performance with the theoretical calculations. Based on that, once if the performance is satisfactory, then we will produce some of the production machines so that we can produce the multiple types of the wind turbines for the future use. Okay. So these are the different types of the design considerations of the horizontal and vertical axis turbine. The details of all this type we will see while dealing with the design of these wind machines in the unit number 6. Now, the next topic from this the next topic is the wind the power equation. Okay, so estimation of the power output. Okay, so this is very interesting. So we know that whenever the wind is flowing, okay, so it is having some certain kinetic energy. Okay, so there is a kinetic energy of the wind is there, and that kinetic energy then it is converted into the power. Okay, so using our wind turbine. Now the kinetic energy it is given by half mv square, where E denotes the kinetic energy in joules. Okay, the m is the mass in kg and velocity is in meter per second. Okay, now what is the wind power equation? So we know that the power this power it is given as the mass this is what the energy per unit. This is the energy per unit time. So energy per unit time. So that gives us the power. Okay, so power it is calculated as the this is the energy. So okay, so this is the same thing. There is a half mv square. So this will become the m dot then when we'll take that so then mass will becomes in the kg per second, and this m dot is what this is m dot we'll calculate as a rho a v. Okay, so this is the formula for this the mass flow rate. So that is equal to rho a v. So this is E is what this is the swept area of the turbine. So this is the these are the blades. Okay, and this area is called the swept area. This is the velocity of the wind. This is the density of the air. So when we put this rho a v, so this is rho, this is pi r 4 d square or pi r square. This is the swept area. So rho a, and then we have the velocity. Okay, so here velocity is not mentioned. So this is velocity is what rho that is the v cube. Okay, so that v square from here and v from the mass flow rate. So it becomes v cube, and here there is one the parameter that is called the CP. So CP is the power coefficient. So this is the power. This is the power in the power in the wind. So this is the wind power. Okay, so this is the wind power that is there. Okay, so that is calculated using this equation. So this is the main equation is it is equal to, this is power is equal to half, this is rho a v cube, and we will multiply it with the power coefficient. So we'll see how this power coefficient come into existence here. Okay, because the this is deals with this will do the the Bayes limit. Now, when we plot this, the power versus the wind speed, so will find that when the wind is flowing over the turbine, so when the wind speed it reaches to some particular speed, that speed it is called as the cutting speed. Then only then the rotor of the blades. Okay, so the blade starts rotating. Okay, the blade starts rotating. So the speed of the air at which the blade starts rotating, it is called as the cut-in speed. After that, the power it is the power increases, and then it comes to one of the fixed value. So we'll call that as the rated power. Okay, so this is the rated power from the turbines. Okay, so then it will not exceed above this rated power. Okay, and the velocity at this rated power, it is called as the rated output speed, and this is comes out to be at 14 meter per second. Okay, so the blades of the wind turbine it start rotating at the velocity of 3.5 meter per second, and that speed is called as the cut-in speed. The power start increasing, and it reaches to some maximum value, and at maximum limit it is called as the rated output power. The velocity at that rated power it is called as the speed at that the rated power it is called as the rated output speed, and the value of that rated output speed is 14 meter per second. Then after that, the power generation remain constant, and at the speed of 25 meter per second, then it is called as the cutout speed. The turbines stop producing any power, or it gets shut down. Okay, it shut itself down. Okay, because after this 25 meter per second, so it is very harmful to operate the wind turbine. So that's why it is called as that we can operate the wind turbine up to 25 meter per second, and then that speed is called as the cutout speed. Okay, so this is the PV curve, that is the PV curve, that is the power and the velocity curve for the wind turbine. Okay, after that we will see what is my Bayes limit. Now, Bayes limit means what? Now, suppose we have the wind turbine, it is rotating. This is the swept area A. Okay, so this is the total swept area A. Vi is the inlet velocity, and V is the outlet velocity after passing over this wind turbine. Now, we know as we will see from the diagram, so the inlet velocity is higher, and after passing through the wind turbine, so the outlet velocity, that exit velocity decreases. Okay, so and at the rotor, the velocity of the turbine, so Vt is equal to the average of Vi plus Ve by 2. So we'll get here the average velocity at the rotor, at the turbine. So that is the Vt is equal to Vi plus Ve by 2. Okay, so here the mass flow rate becomes now rho a V. So V means it is Vt. So Vt is equal to Vi plus Ve divided by 2. Okay, so mass flow rate we have here mentioned here. After that, what will happen? Now, when we that means when we take the relation, that means when we calculate the power from power in terms of the velocity component, that is exit velocity divided by the inlet velocity. So the power will get some power curve, and we found that when this exit velocity is equal to, that means here the velocity. Okay, so when the velocity here VE is equal to, when it becomes Vi by 3. Okay, so at this particular condition, the power generated by the turbine is maximum. It is found that the power generated by the turbine is maximum. Okay, so this is that point where you will get the maximum power, and the value of that VE becomes, it is exit velocity becomes inlet velocity divided by 3, and at this particular condition will get the maximum power. So it comes out to be the 8 by 27 rho a Vi cube. Okay, and we know that the input power is what? It is half rho a Vi cube. Okay, so that we have seen in the initial slide. So in the input power is half rho A VIQ, okay, and the maximum power generated at a particular condition of VE is equal to this is VI by 3, okay. So this condition VI by 3 or 1 by 3 VI. So we'll get the maximum power, that is 8 by 27 rho A cube. So here we will find out here the maximum efficiency. So maximum efficiency is equal to the P max divided by P in. So we'll get the ratio of here. If we multiply, if we divide this is P max divided by, that is output power divided by the input power. Okay. So here we'll get the P max will come here and P in will come here. Okay. So if we divide this P max 8 by 27 rho A VI cube here and the half rho A VI cube here. So we'll get here 16 by 27. So other things will get cancelled. Okay, this get cancels here. Okay, and we'll get here, this is multiplied by 8 multiplied by 2, 16 and 27. So we'll get here 16 by 20, 16 by 27, or that comes out to be 59.23. Okay, so 59.26%. Okay, or 5.593, or this is also denoted as a 0.593. Okay, so this is the maximum efficiency that is generated by the wind turbine when the exit velocity is the 1/3 of the inlet velocity. But this is for the ideal conditions. This is only for the ideal conditions. Okay, this is the velocity calculated at the ideal condition, and this velocity, it is this maximum this efficiency, it is also called as the power coefficient, or it is also called as the Bates limit. Okay, so Bates limit, it is what? It is 0.593 or 59.3%. Okay, so that is called as the Bates limit. That's why, whenever we calculate the power for any turbine, any commercial turbine, so it is multiplied with this power coefficient, because we always get less the power than the 59.3%. Okay, so commercial wind turbine, it produces the power in the range of 40 to 50%. The efficiency of wind turbine, it is always less than 59.3%. Okay, so most of the commercial wind turbine, it operates in the efficiency of only 40 to 50%. Okay. Okay, so this is regarding all the Bates limit. Okay, then we have some of the examples. Determine the power in the wind if the wind speed is 20 meters per second. So here V is given, and we have blade length is given here. So blade length, so that is equal to, that means we have, this is the blade length. So this length is given. Okay, we have this area. Okay, so this blade length is, this is 50. So this is diameter become, this also become 50. So this is total, the diameter becomes 100. Okay, so we have to calculate here the power. We know that the power formula is this one, half rho A V cube. Okay, the power in the wind. Okay, without considering that Bates limit. Okay, so here this is the everything is given. So density of the air is 1.23. Then the area is calculated as pi r square or pi by 4 d square, and the velocity. So we'll get the answer in watt. Okay, so similar type of the example it is given here. So here this is the speed is given 10 meter per second. Okay, so velocity is given. Again here blade length is given, so that is becomes our r. When blade length is given, so that is our radius. Okay, so if you are using the formula for the area, that is equal to pi by 4 d square. So you have to take the diameter as multiply by 2 here. So this is 40. Okay, that comes out to be 40. Again, the same formula for power, P is equal to half rho A cube. Put everything here. Density of the air 1.23. Then kg per density is equal to mass upon volume. So that is kg per meter cube. And the velocity. Okay, so that velocity we have to put here. So once here it is V cube. So 10 raised to power 3. So that comes out to be 772,200 or 772.440 kilowatt. Okay, so this comes out in watt. So sometimes they will give in the answer in kilowatt also. So here this is 38.622 kilowatt, and in this case this becomes 772.44. Divide this value by 1000, so you will get the answer in kilowatt. Okay, so be ready with the watt and the kilowatt answer. But whenever you put all these things, that means when you put density, the density in kg per meter cube, area in meter square, and V in meter per second. So answer comes out to be in watt. Okay, so that answer there. So this is regarding the calculation of the power. Okay, so we will expect this type of the simple example in the examination. Okay, so this is again the same thing. These are the different types of the blades. The comparison of the different types of the blades are given. So 2 blades, 3 blades, and multiple types of blades are there. Generally, there is a question. There is general question why we are not going for, we are going for 3 types of blades and not for the 4, 5, 6 type of the blades are there. Okay, so here in case of the if you see the 2 blades, they generate low torque and they have a higher PM. Okay, and the comparison is made on the same power. They will if we are using the 2 blade, they are making more noise. Okay, but since these are cheap, okay, so we are using this type of the turbines the offshore that means in the water, in the oceans. Okay, so we are using this type of the wind turbine or the 2 blades system, wind turbine system in the in the offshore. Okay, since it is cheap, we can easily we can manufacture this one and we can put it in the offshore. Now why 3 blades? So the 2 blades is having it is producing more noise, so we can't put it in the residential area. But if we put the 3 blades, so it generates the less noise. So that's why the wind turbines with 3 blades are mounted in the residential areas. Okay, or nearby residential areas. Okay, so or on the hill areas or the onshore. Okay, onshore wind turbine. We call it as the onshore wind turbines. So this is because of the characteristic of its less noise. Okay, if you are using the multiple the blades, if you are using the multiple blades, so then it is having no noise, but it is having the high torque, and because of this high torque, we are using for its various functions such as the wind pumps. So we can use this in agriculture, agricultural purpose, or in the areas, in the hill areas, to pump the water. So for water pumping, this application, generally the wind turbines with the multiple blades are used. Okay, so this is the comparison of or the selection of the turbine based on the blades. Okay, so based on the application also. Okay, so these are some of the parameters on which we can select the types of or the number of the blades for our wind turbine. Okay. Okay, so then this is all regarding the today's content. So I hope you understand this one, and we will, that means we will cover the next part in the next lecture. So thank you very much.